Welcome! Today we're walking through pull request 24908, a significant addition that brings MiniMax M3 sparse attention support to llama.cpp. This is a big architectural enhancement spanning 15 files with nearly 2,000 lines added. Let's start with the big picture. This PR has two primary goals. First, add the full MiniMax M3 model architecture with its sparse attention mechanisms. Second, implement a new indexer key caching layer in the KV cache to enable MSA block selection. Beyond that, we're adding slot invariant enforcement, multi-stream support, new indexer parameters, and making sure dense attention still works as a fallback when sparse mode isn't available. MiniMax M3 is a new family of models with sparse attention that goes beyond existing indexer support. The current DSA architecture retrieves indexer keys on demand, but MSA requires those keys to be cached alongside K and V tensors in the KV cache. MSA also needs blocks anchored to absolute cache slots, per GQA indexer heads, and strict position to slot invariants. This PR lays the complete foundation to load and run these production model variants. Here's the change surface. The heart of the work is a brand new 562-line minimax-m3.cpp file implementing the full architecture. We've got substantial updates to the KV cache header and implementation for indexer key management, plus conversion tooling in Python to extract sparse config from model checkpoints. The rest is wiring, architecture enums, tensor mappings, metadata keys, and test fixtures. Let's look at the KV cache changes first. The cache used to allocate just K and V tensors per layer. Now, when a model has an indexer, we allocate an additional K_IDX tensor. These are F32 tensors sized by the indexer head dimension and the KV cache size. This is the storage foundation for MSA block selection. Indexer keys are cached and reused across multiple inference steps. MSA introduces a strict invariant. Cache slots must exactly match token positions. This is enforced during batch application. If we're in MSA strict mode, the code walks through each sequence and asserts that every slot equals its corresponding position. This guarantees that blocks are anchored to absolute positions in the cache, which is critical for MSA's block selection logic. Now here's the heart of the new architecture in MiniMax M3.cpp. For MSA layers, we project and normalize the indexer Q, retrieve cached indexer K from the KV cache, then compute block scores by matmul. Those scores get reshaped into blocks, max pooled, and fed into a custom op that selects the top K blocks with optional local bias. The resulting mask is passed to flash attention, which only attends to the selected blocks. This is multi-stream, sparse attention in action. On the conversion side, we've added a MiniMax M3 model class that extracts sparse attention config from the model checkpoint. It pulls indexer_block_size and indexer_local_ blocks from the hyperparameters and writes them into the GGUF metadata. It also bakes Gemma-style RMS norm weights by adding 1, which matches how M3 models store their normalization. This ensures the GGUF file has everything llama.cpp needs to configure the architecture at load time. After this PR lands, llama.cpp can load and run MiniMax M3 sparse attention models end-to-end. The KV cache now holds indexer keys alongside K and versus MSA layers compute block scores, select the top K blocks with local bias, and perform attention only on those blocks using flash attention. Dense layers and fallback paths still work exactly as before, so there's no regression when flash attention isn't available. And the strict slot position invariants prevent cache corruption during MSA operations. Let's talk about the risks we found. There are 7 concerns scattered across impact and likelihood. The most severe are the MSA slot invariant abort and the SEQ_RM rejection crash. Both use hard aborts that could be unrecoverable if triggered. The silent dense fallback and late block size assertion are medium impact. The RMS norm baking assumption and a few silent validation gaps are lower but worth noting. Let's zoom in on a couple of these. The first concern is the MSA slot position invariant check. If a slot doesn't match its position, the code calls GML_abort, which is unrecoverable. This should never fire under normal operation because find_slot explicitly builds matching slots when MSA strict mode is enabled. But if there's a bug in find_slot or an edge case in cache management, the process aborts. Consider whether this should be a logged warning with a fallback instead of a hard abort. The other notable risk is in the conversion script. RMS norm weight baking adds 1 to all norm weights unconditionally, assuming all M3 models use llama-style RMS norm, where weights are stored as 1 plus W. If a model variant uses plain RMS norm without this offset, the conversion will produce incorrect weights. There's no safeguard or model variant detection here, so this is an assumption that holds for current M3 models but could break with future variants. Alright, that's the walkthrough. This is a well-structured architectural addition that brings MiniMax M3 sparse attention support to llama.cpp with clear invariants and graceful fallbacks. I'd recommend approving with a couple of notes. Consider replacing the hard abort in the slot invariant check with a logged warning and fallback, add model variant detection for the RMS norm baking, and move the block size validation earlier to model load time. Overall, really solid work. The foundation is clean and ready to support this new model family. Nice job!